so we'll first start with our end goal. This is what we know to be truth because of our class and our textbook as the Lagrangian equation of motion that comes from saying L, the Lagrangian, is equal to the total energy minus the potential, some potential V. And the way we get actual usable results from this is by using our Lagrangian L and plugging it into these various differential equations with some coordinate k, some coordinate q, subscript k. You'll have to excuse me for that error. Now, let's talk about how we get here. So we're going to start with Hamilton's principle, something expressed in chapter 10 that'll leave us with the first differential equation that relates some partial derivative of j to the partial derivative of the time integral of L, which is some path. With that as our starting point, we can now move on to understanding what the coordinates are, and the coordinates velocity, which is right here, that q dot k, we can understand what they mean if we evaluate this time integral right here. So expanding it, we can get something that looks a little bit like this. T2, T1, and then a full summation over time of this wonderful, wonderful mess of symbols that I find very, very fun. QK, that's the partial derivative of QK, plus the partial derivative of L, our Lagrangian, over the partial derivative of the coordinates, the generalized coordinates velocity right there, with respect to the velocity's partial derivative, all encapsulated by that dt here, because again, this is still a time derivative. We'll set that equal to 0. Now, the q, all of the q's are a function of time. They change as this system evolves in the time integral from t1 to t2, hence our bounds. Therefore, the variation, which is this dq, this delta q, is equal to the difference between the two slightly differing functions of time, time being t. Then we can express the dq dot as something very cool and very different, which will help us out. So if we say the partial of q dot k is equal to the time derivative of just the normal qk, which follows, again, like we said, this is our generalized coordinate system, and this is the velocity of said generalized coordinate system. Then we can substitute this into the last term of this equation right here, and then integrate by parts to obtain this. Now, I'm integrating by parts here, as in it's been done already. So I'll skip this for time because I would love to spend 20 minutes on this. Fortunately, I'm condensing this to 5 to 7. So let's evaluate this. So, still in our time integral here, from t1 to t2. Bring back this enormous summation of the partial of L with respect to q dot k times the time derivative of delta q dt. Oop, my pencil. Now equals the full summation of the partial outside with respect to dqk and dqk. Now evaluated at the boundaries, so employ our boundary conditions of t2, t1, minus, this is where we did integrating by parts. We have another integral now, so we have to subtract another time integral of another summation of the time derivative of the partial of L with respect to the partial of q dot, another respect to just the partial of q here. So no q dot there. That's what we're evaluating. And again, that dt that we take now. And now, what's wonderful about this result is that we can integrate, the integrated term in the brackets will vanish. This is the really satisfying part. It will vanish because the variation in the dq right here is 0 at the endpoints of t1 and t2. So applying these boundary conditions, we'll find out that this part right here becomes 0. That means we're left with the partial of the entire integral of the Lagrangian with respect to time equals the integral, another time integral, of the summation of time to this now synthesized wonderful bracket. That's the partial of L QK minus the time derivative of the partial of L Q dot K. Now we're starting to see some similarities between here. Maybe you can see where this is going. Well, of course, you're the professor, you know where this is going. All with a partial QK over time equals 0. Now, each QK is a generalized coordinate, and it's independent of every other QK that's involved. So each variation is independent as well. The actual value of each variation is completely arbitrary then, since they're all independent. And we can vary each coordinate in any way that we want to choose, so long as we make sure its variation vanishes at the boundary conditions at T1 and T2. So at the endpoints of the path, as long as the variation is canceled at the end of it, as long as it vanishes, then we're fine. We can make this work. The only way we can ensure that the integral vanishes, giving all of the infinite possibilities of variation for the DQs, is to demand that each bracketed term in the integrand vanishes separately. So let's work this out in math. So if they've all vanished separately, that means that the partial of the Lagrangian with respect to just QK minus the time derivative of the partial of the Lagrangian with Q dot K, that's this part right here, equals 0. So that means there's no variation at the endpoints. That has 0, and our Lagrangian equations of motions work, and they follow this. And look what we can get here. We've already proved it. So we found this. If we do a quick addition, we can get that partial L over partial QK is equal to the time derivative of partial L over partial QK. And then we have derived the Lagrangian equation of motion, the Euler Lagrangian equation of motion. And yeah, this works for a conservative system, for any equation of motion. And it is subject to only holonomic constraints, which is meaning as in one number constraints, which I think is fun. And I'll talk very briefly about the applications of this. But here's our lovely final answer after going through the proof. After that very long-winded derivation, that proof, let's talk about some applications of the Lagrangian, and specifically why I thought it was so fascinating and useful in life is that with the Euler-Lagrange equation of motion, you can systematically derive equations of motions for anything with a Lagrangian, with that L equals T minus V. So as soon as you have a Lagrangian defined, your equations of motion can be obtained relatively easily compared to directly applying Newton's laws, for example. Some examples that I've compiled are simple pendulums. You can describe their motion with a Lagrangian approach and capture its behavior once you know the Lagrangian, and you can apply these differentials. A double pendulum, same thing. It has non-trivial constants, which you can use Lagrangian mechanics for to provide a pretty efficient solution rather than Newtonian. And rolling motion, falling motion, any conservative system that you could think of. A crazy example, perhaps, a rolling torus, a rolling donut. If you dropped a donut down a slide that has a pearl inside it, and it's pearl sliding inside of it, you can attach a Lagrangian to this. You could find the Lagrangian, and then find its equations of motion using this. Incredibly useful in the rest of my life. Something I'll both remember 5 to 10 years from now, I'll use for the rest of my life, and something I find very, very fascinating. Thank you so much for listening, Professor.